Hello, everyone. Welcome to the reading group this week on April 15th, and I'm going to be presenting Mongrel, which is a paper on hybrid techniques for standard cell placement. This came out in the year 2000, and it is a pretty interesting paper. They have a lot of very interesting techniques, and I wanted to kind of talk about this because this isn't quite analytical placement. It isn't quite not analytical placement. It's kind of a hybrid in between. And you can see elements of both within their approach. So I wanted to show that for today. Hang on, let me just get this pinned and then that makes it easier for me. Okay, cool. So this paper actually came out. So there was a paper that came out before the Mongrel paper, which is called Relaxation and Clustering in a Local Search Framework Applications to Linear Placement. This was then updated in 2002. This paper contains a lot of the proofs from the Mongrel paper, but it's a slightly different algorithm. I just wanted to mention that it exists, and I'll make reference to this in some parts of the Mongrel paper. But in this presentation, we're going to be talking about Mongrel, which came out in November of 1999. So this comes out of the University of Illinois at Chicago. So let's get right into it. Can I close the door? Thanks. So so I just want to give a general overview for placements for A6 standard cells because some people might not be familiar with that. So we have a net list, which we're all familiar with, represented by a hypergraph of cells and nets connecting their inputs to outputs, very similar to the FPGA CAD problem. But in difference here is that cells have a fixed height because we're dealing with standard cells, but they have variable widths. So for example, an AND gate versus a much more complicated gate might have different widths because they have more transistors inside of them. So we have different size blocks, and our goal is to find a placement for all of these cells that minimizes the amount of wiring needed to connect the cells, subject to the cells cannot overlap. You can't have two transistors on top of each other. And you want to split them into roughly equal sized rows. And so this is just the preliminaries of like what we're trying to do with placement. Sounds good? So what is this hybrid technique that they speak of in the title? How is that different from the other techniques that we've talked about in these reading groups? So in this paper, they classify each prior technique by their view of the placement of the problem space. So what they call top-down techniques, which they say is recursive bisection and analytical placement, this is techniques that have a more global view of the placement problem to make decisions. So they try to get the general shape. Because they're looking at such a big problem, they tend to relax the constraints. So they don't have the fine-grained details that like this block wants to be right next to this one, but it gets the general gist. Flatter techniques, as they call it, are things like annealing-based methods, which have a more local view of the placement problem to make decisions. So for example, they have the true constraints, for example, and they know that if they swap these two blocks, it will improve or not improve. But again, because they have this more flattened view, they can have more constraints, but they have a much harder time, so they have to do it on a smaller subproblem. In this paper, they propose a hybrid technique, which is what they call the middle down technique, just more alphabet soup. And it uses both global and local optimization techniques during their global placement. And they also use it a little bit in their detailed placement, but their detailed placement is kind of interesting. So we'll talk about that today. So that's what they mean by hybrid. It's not quite analytical placement global view. It's not quite annealing local view. It's kind of a mixture where they kind of jump in and out of global versus local views of the problem. And I'll make that clear when we get into the algorithm. Cool. So this is one last preliminary before we get into the actual algorithm. They make a distinction between a global and a detailed placement solution for standard cell A6. So the Mongrel creates these two. We have the global placement, which is legal if it satisfies the bin capacity. So what we do is we take our placement, or our region, we break it into rows, which is just from the problem. We break those rows into bins, and our goal is to make sure those bins are not overfilled. Now, this is a lot like analytical placement in VTR, where we're not going to, we're not going to enforce, because we can't have overlap, but for the global placement, let's ignore that overlap for now. Let's just say that bins can't be overfilled for now. And finally, the row size constraint, all rows have roughly equal size. That's the goal of global placement. It doesn't, those are the legality constraints of global placement. And again, we're ignoring cell overlap so we can get a better solution, or at least we can solve a good solution globally. This is similar to AP, where we may relax some constraints to obtain a global solution. Detailed placement, it's legal if no two cells overlap and the row size constraint is satisfied. And by construction, this also means that the bins are not over capacity. So by doing this, it's actually a stronger legality constrained placement than the global placement. And this is similar to AP, where we have a fully legal placement, or AP for FPGAs. So these are the two placements that we're going to be working with in our flow. We're going to start with our global placement, which we've relaxed some constraints so we can do some optimizations. And then we're going to turn that into a detailed placement and do more optimizations. So these are just some nomenclature we're going to be talking about from this paper. So here is the overall Mongrel flow. So now a little bit of an aside. This paper was written like, it feels like it's written top to bottom to top. So this algorithm actually comes at the end of the paper, which makes it way harder to understand what the algorithm is doing until you've read the paper once. So if you do end up reading this paper, I recommend actually maybe skipping to the Mongrel flow section and then coming back to the beginning. So that's why I've structured the slides in this way. I just thought it was funny. So the Mongrel flow works like this. We start with an initial legal global placement. Notice this is different than other flows. We're not trying to construct a global placement using our global placer. We start with an initial global placement, which we got. I don't even remember if they said it in the paper where they got it from, but you just get an initial global placement. We optimize the global placement while remaining legal. And we're going to talk about their Rebels algorithm, the relaxation-based local search. And then we transform the global placement into a legal detailed placement. And then we optimize the detailed placement while remaining fully legal. That's their general gist of their flow. And we're going to talk in depth about this, but this relaxation-based local search is going to take a part of the legal solution, pull it out, optimize it using analytical type techniques, and then re-legalize just that small subsection. And an overarching theme from this report, from this paper, is that they will only ever make choices that improve the placement. So for example, if they call Rebels and it made the solution, the current placement P worse, it actually won't accept it. So it consistently only makes decisions that improve wire length. And I'll show you more about this as we get into this algorithm. Any questions so far on the overview? This is just a standard thing for analytical style placements. We have a global placement followed by a detailed placement. So how does Mongrel do their global placement? I want to walk through this algorithm because it's kind of cool. So here's what we're going to do. We're going to randomly select a subset of the current placement where there's M nodes and make them movable. Now, over several iterations of global placement, we're going to make M smaller and smaller and smaller. But for right now, we're going to select a subset of M nodes, and we're going to declare that those can move. We're then going to fix any nodes that are touching those movable nodes, because those are the ones we care about. Any fixed nodes outside of that set, we don't care about, because they're not actually going to contribute to anything that's going to happen in our placement right now. And then we're going to solve for an ideal HPWL placement. And they do this using a network flow-based approach, which I'll show you how they do that. And then once they have that ideal placement, that's going to be super illegal. We're going to have so many bins overfilled, it's going to be crazy. So we're going to legalize this using a ripple flow, which is one of the reasons why this paper is known, is because of the ripple flow technique, which we will talk about. And finally, they do one last little cleanup, which they optimize further using an FM partitioner. So that, and the key idea, and I'm going to keep talking about this, we always maintain the best global placement solution found so far. That's what this is saying. If the wire length improves, we're going to reset our counter, and we're going to take that as our current placement. But if it did not improve, we're not going to accept that placement P prime, and we're going to just decrement this counter. And so basically, we're just going to keep grabbing a subset, optimizing, grabbing a subset, optimizing until we have converged on, until it doesn't improve after k iterations. How do they grab the subset? I didn't mention this in the paper, in the slides. What they do is they randomly, literally randomly, select a net in the net list that has a fan out less than or equal to m, and then they add all of the nodes on that net into their that set M. And then if they don't have enough yet, they'll then start looking at those neighbors again randomly. So they make it very clear it's random, and the results will show that I don't even think, like, I'll show you what they say in the results. Their results actually give like a best of 10 value, and they give an average of results. So I assume they give it different seeds. So I'll show that as well. But again, it's basically just random select points that are connected to each other. Any questions? I'm gonna go in depth on each of the steps.
Okay. And the connector probably matters, right? Like,
oh yeah, definitely.
They're making sure that they've got things that have something in common.
Yeah.
And I guess you talked about this next, but they like unlock those, solve the like an analytic equation,
yep,
basically to figure out where I'd like to put them and then repeat blocks.
Correct. So we'll get right into that. So yeah, the randoms.
Like a different way of like, instead of saying I'm gonna cut up things and make things legal that way, it's like I've got something legal, like let's move around some stuff.
Correct. And so this feels a lot like a detailed placer. It just feels like a detailed placer because we're starting with a legal solution and we're going to, they call it like they're going to move to a different solution and only move in that direction if it actually improves things. And so that's what they're trying to show here. This is a little different than how we normally do things in analytical placement, but it's not necessarily that different. So I like their ideas. So let's talk about their optimal relaxed placement. So what we have is we've taken our graph and we've created a subgraph of m movable blocks, and we want to minimize those m movable blocks HPWL relative to the fixed blocks that they're connected to from the previously legal placement. And it's this equation. Now, I wrote this equation down when I took the convex optimization course, and I didn't know if anyone else has done this. They did it, and they wrote it in the paper in the year 2000, around the year I was born. So they probably stole it from me. So how to read this? We have two slack variables, or I say two. Each net has two slack variables, R and L. And those are defined by these constraints. They're the bounds of the net. Every single node must be larger than or equal to the leftmost value, the L slack value of each net, and it must be less than or equal to the R value of any node in that net, or any, yeah. And the idea is that as I minimize this LP, the R and the Ls will get closer and closer inwards until they've created the HPWL equation. And this is only in one dimension. Because X and Y are linearly separable, you do the same for the Y dimension. And this last one is just all fixed blocks are fixed to their fixed locations. So this is how you can represent the minimization of HPWL into a LP problem. And you can solve this using an off-the-shelf LP solver. The issue with off-the-shelf LP solvers is they're polynomial in runtime, but they're still very slow, especially because, recall, the number of variables is obviously the size of m, but we also have a number of constraints, which is proportional to the number of edges. So our constraints are actually, because in graphs for circuits, the number of edges, the number of hypernets is actually very, very large. The number of blocks is also very, very large. So it's not very efficient to solve that LP. And so it doesn't scale very well with the circuit size. But can we solve this more efficiently? And that's what they propose in the prior paper, which I talked about, that came out a few months prior. So we're going to use some good old-fashioned graph algorithms. How does it work? So in a prior paper, the authors show that we can efficiently compute this LP, and this particular LP, not all LPs. They're focusing just on this one. It's based on a network flow where they use an augmenting paths algorithm, finding the min cuts in a flow graph. And I'll step through the algorithm in a moment. The authors prove that this will find an optimal solution. Now you have to go into the 2002 paper to find that proof, and they call it a proof sketch instead of a proof. So I just thought that was interesting. And they claim that an instance of 5,000 mobile nodes and 1,000 fixed nodes can be solved in 8 seconds, whereas a regular general LP solver will take 55 minutes. And also for context, our largest circuit, which I believe is DirectRF or on the order of DirectRF, is 500,000 mobile nodes-ish. So just something to keep in mind. And others' papers show that the min cut step, I'll put a little asterisk here, I'll explain that in a second, can be solved in big O of V times E time for this problem, where V is the number of movable plus fixed nodes and E is the edges. Now, I put an asterisk here. The min cut step itself can be solved in big O of V times E, assuming you did some pre-computation. And I did not find the time complexity of the pre-computation, but the paper that talks about this, and I'll show the citation at the end of the slide deck, did mention that there's some pre-computation that goes in to basically find the augmented paths. But the idea is that you can reuse the augmented paths from prior iterations. Really complicated, but the actual algorithm is pretty straightforward. These are our fixed blocks, and these are our movable blocks. Everything is in the X dimension right now. Y dimension is independent. We're going to start from the left and work our way right. So we're going to create a partition line, and this one's right in the middle of the algorithm, but let's say we just started the algorithm. We're going to create a partition line that partitions from the first fixed blocks from all other fixed blocks. And everything, all the fixed blocks on the left, we create a fake source node and make their capacities infinite. This is a flow graph. And the capacities of all edges within the graph, they have this fancy scheme where point-to-point connections create 2 directed edges of each capacity 1. Read the paper for details. But the idea is that I go from left to right and find the partition and partition the nodes. Anything that shows up on the left partition and is just grazing against it will then be put at the same X coordinate as the fixed block. And you go from left to right. So that's what this is saying here. We're going to create our S and T. We're going to find the leftmost min cut using any flow algorithm you want, and they mentioned one in their paper. You grab all of the elements of A that are not fixed, and you check the ones that are to the left, that are not in the left. Basically, the ones that haven't been marked yet. So any unmarked nodes. And then what we do is we assign the position of all of these nodes that just got moved. So for example, let's imagine the first partition was right here. So these 3 nodes have already been placed. And then I create the second partition right here. We're going to take these 2 nodes that weren't put on the left prior. We're going to lock their positions into this fixed blocks position. And then we are going to add them to the set of nodes that have been placed. And as you move from left to right, the authors argue that this will achieve the optimal LP solution. And as I said, this, according to some other papers, this min cut step can be solved in O of V times E, and we do this for F times. So, and F, let's say, is on the order of V. So therefore, this will be V squared E. So not a super, it's not, it's, so for FPGA CAD problems, we want N log N. That's just a good one to have.
N is better.
N is better, obviously. O of 1, actually. If you already know the answer, just tell me, man. But N log N is the slowest we would accept. N squared is just, it's fine for smaller circuits, but with the circuits we work on, that squared becomes just absolutely ridiculous. So this is becoming V squared times E, and the number of edges is on the order of the number of vertices usually for our graphs. So therefore, this is really N cubed. And that's just a minimum because, as I said, there's probably some pre-computation going on here, which I think is N cubed log N, but I'm not sure. The paper didn't really make it clear, and I didn't read it that intently. But yeah, it's a really interesting algorithm because it's much more efficient than using a general off-the-shelf LP solver. The other thing I want to draw notice to is there are no net weighting here. And I can't figure out if it's even possible to add net weighting to this formulation. They do make all the capacity of all the edges one here, but I'm not sure if you multiply them by some weight, does that actually work? Because of how this algorithm is laid out, I don't think the proof works on getting an optimal solution if you had net weighting. And so if you tried to use this in our AP flow, I predict it may not be able to, won't be able to add anchors, at least not in the way we've done it before. So that could be a problem. So I just thought I'd mention that.
Let me see if I understand this. Okay, so I mean, the way they're controlling complexity is they don't make too many unfixed nodes. So they take some set of unfixed nodes, not too huge. Everything else is fixed.
Well, actually, M starts as the size of the chip and then goes down smaller and smaller.
So they start with it really big.
Let me just double check the exact size they started at, but
Maybe just completely unusable for.
oh no, they have an alpha term, so you're probably right. They do have an alpha term, maybe that's 0.5. Actually, they wrote it in the paper somewhere. At the end, I can show you the exact numbers they chose.
Okay, well, even if they make it big, that is a parameter that can be used to control
Correct.
how expensive this gets.
Forgot about
Or
that.
solve. Okay, so they've got a bunch of fixed things, they got a bunch of removable things. The source is connected initially to all, like, where source is connected to the fixed blocks, you said.
Let's start
What
with,
about T?
so let's start with this. At the beginning of the algorithm, all fixed blocks are connected to T, all of them.
All of them are connected to T initially.
Yep, and then when we start, we look at
That
the,
says connect them to S. On your right, is it?
so create an edge FT with capacity for all FIs equals this. So this one right here at the beginning.
Now look at the comment, initially connect all fixed nodes to sync.
Where?
Just above the create an edge.
Maybe their comment's wrong. Okay, I'll just read the comment.
Oh yeah, that is not mine. Initially connect all fixed nodes to sync. Yeah. Well,
T,
so this is source and this is target, I think. I think they're,
so that's all the fixed ones, right?
yep, so we take all the fixed blocks and we connect them to T.
Oh, sync is T, right?
Yeah. See, this is a sync because it's syncing values.
Yeah.
It's just it's not
No,
S
I'm
and
saying
T.
like S for thing, you're right, S for source. Okay.
It's actually, yeah, it is a good, that's actually not good. But
So initially the connector was T.
yep,
Okay.
and they go from left to right here. This is important. So this is going from this F to this fixed to this fixed to this fixed.
Okay. Delete one edge
Yep, which is the edge from T to the fixed block.
and then add an edge to the source instead.
Yep.
Find a min cut, okay. Then say, A is.
Here, I can
It's just the left partition of their cut.
A, I believe you are correct. Oh no, A is the left partition. Yep, the leftmost min cut. This is the left partition, I believe. And you say everything that's not fixed in the left partition and that we haven't fixed yet. So let me just show you.
Take all the fixed things.
Yeah, so let's say I chose this partition originally in the prior iteration. I'm going to
Okay.
fix this one and this one, for example, to be at this fixed location. And then I'm going to add them to the left set. Now, when I'm on this partition line, I put these two as on the left side, and they haven't been assigned a fixed location yet. So these ones are going to get assigned to this fixed block.
Oh, it's the whole thing. Okay, so they just take out the fixed points, then they basically say new is just A with left removed. So
Yep.
A, it's the right part of A.
Yep. The right part of A.
Because they just took out left,
So-
I think, according to the notation.
They took out left, which are these three, for example, which were from the prior partition. It's basically what was on the left side in the prior partition. That's what left is.
Oh, okay.
They just build it up over time, as you can see.
Okay, so initially new would be left is old, got it.
Yes.
XP equals P minus one by. P minus one, what's P minus one?
Yeah, no, I don't like this notation. It's just the position of the fixed block.
Okay. That's what you're saying, tie it to every fixed block that's connected.
Yep, for this particular fixed block that we are at right now. So this one. I believe it's this one. It wouldn't be this one, or, I'm actually, yeah, no, it would be this one. So yeah, it would be this one right here. In this iteration snapshot. And how they build this flow graph, they talk about in another paper. They don't even mention it in this particular paper.
Yeah.
But it's interesting. And also how you hand out, they don't just set it all to one because you also deal with hypernets. So they actually create fake, like not quite star nodes, but they're basically star nodes, and they connect them all up in that way. You can read the paper for the nitty-gritty details. Any other questions? It's a very interesting formulation. It is definitely faster than true LP. It's just, yeah, it's different. I think, I'm not sure if bound to bound is still faster. You'd have to check that, but just an idea. Okay, so now the fun part, legalization. So we've just found the minimum LP solution, but as anyone who's worked with the LP solution before, everything goes around top of each other. So now we need to legalize the solution. So how do we do this? What they do is an iterative node rippling procedure to legalize the global placement. Recall, we start from an initial placement, initial global placement. What we're going to do is we're going to take our initial global placement and we're going to select one of the unplaced movable nodes from the movable node set M. We're then going to place that node. We're going to move it from its legal position currently in the placement, and we're going to move it to its optimal solved position, or at least as close as it can get. I didn't make that clear. If after making that move, if there is an illegal bin S anywhere in my placement, find a target bin T that a cell can move to legally. That doesn't mean that this cell can move to it. It's just something next to it can be moved into it. And then we're going to ripple move cells from bin S to bin T. And I'll explain what all this means in the next slide. And then we're going to repeat this step. We're going to say, okay, are there still illegal bins? Yes, let's do another ripple move. Are there still legal bins? Yes, let's keep going. And if the new legal placement has a shorter wire length, record it as best. And I do want to make a little note here. It's not extremely clear in the paper, but I think in step two here, when we place the node at the optimal solution, we will always use the best recorded placement. We won't be doing any, I don't think they do any hill climbing here. So I just wanted to make that note. And then we'll actually then repeat step one. So then we'll select the next unplaced node and then the next unplaced node. And we keep going along that list for all nodes, all movable nodes in M. So let me get into how we're actually going to be doing this ripple move, because that's the really important part. Let's imagine we have S on the top left right here, and we have T on the bottom right. Now, how did I find that T is available? I noticed that it has space in it, and there are blocks that can move into it. This block, for example, it can't have blocks move into it because it would then become overfilled. So this is not a target T. The idea is we want to find a T that is closest to S where some node could get moved into it so we can make space. And what we have is this graph here. Now, what are these numbers? They're very important. This cell right here, it could, in theory, move to the bin to the right, or it can move down to the bin below. These numbers are the game. If I took this cell and moved it to this bin, how will the HPWL improve? Well, the HPWL reduced by 3. Therefore, this has a gain of 3. If I took the cell and moved it down, the HPWL will get worse by 3. So it has a gain of -3. And we do this for all the cells, for all the bins in this bounding box between S and T. Okay? We're then going to build this graph. This graph has an edge for the highest gain node to move from this bin to this bin, this bin to this bin. So for example, if I had to move any of these cells, which one should I do? Well, the one with the highest gain. So this has an edge of 3. This one, what's the best case? Well, that'll have an edge of 0, and so on. And here's the important thing. We're only going to allow movement monotonically, meaning we can only move right and down. We can only move right and up. We can only move left and down. We can't go left and then right. We can't go up and then down. We have to go in a monotonic direction. And what we're going to be looking for is what's called the max gain monotone path, which we will go through like this. And the key insight is you can solve this faster than if this was a Dijkstra search. Because this is a monotone path, you can solve this using, what's it called again? Because this is acyclic, you can solve this using, I forgot to put this in the slide. I can't believe I forgot to do that. Here, this is actually really important to why they do this, so I need to make sure I get the name right. Because they use a, oh boy. I apologize for not being, here we go. Since the gain graph is acyclic, we can find the maximum gain path by topological ordering, which is a much more efficient algorithm than, or I say much more, it has a better time complexity than Dijkstra's. So this is why they actually do this. We could have made a gain graph that's much more complicated than this, but we want to make this very, very efficient and very fast. We want things to ripple. And so we'll get into what's going on here right now. So we want to find the max gain monotone path from S to T. This is, if I were to create some kind of conga line where I move things from S to T, who will move from where to where? Where the gain of each edge is the max increase HPL, as I just said. And monotone path means that we can only move right or left and up or down, but you can't go left and right. And therefore, this graph becomes acyclic. Up. And then we're going to move cells with the highest gain along this path. And so a cell that was just moved can be moved again. So for example, let's say I moved this guy, or let's say the -1. Let's say I moved this cell down here, and then I found that, oh, this had a gain of 4, but after I moved this cell down, it's actually really good for the gain to move it to the right. They allow that in this algorithm. And so the idea is that as I ripple move, I'm going to take the best gain value, which is this cell right here, and move it. Then I'm going to look at all of these cells and say which one will have the highest gain to move right. Most likely it's this cell, and then move it, and so on along the path. And the idea is that things ripple in such a way that we can create hopefully a better gain solution or a better HPWL solution. So this is the key insight from this paper. This legalization technique allows us to move cells into their theoretical optimal positions, and then we can move other cells out of the way if we think that they can, if this one that I just put there is better. Does that make sense to people? It's a really cool legalization technique. It's very efficient to compute because again, finding this path is actually not that expensive because topological sorting, I think, is done in big O of V plus E. I think, or is it, I don't remember. I think it's OVE. Hang on.
It'll just be V plus E, it's not.
Yeah, it's not times. So, and it's not V log E because that's Dijkstra's. So therefore it's V plus E, which has a very good time complexity. And building this graph is not that expensive, especially if you somehow cache these gains, which I know for certain they're doing. So that's for sure. So any questions on ripple moving? Here, let me get a picture just so that it makes a bit more sense. The hacker website or whatever.
Basically means you process a node once all its inputs. The good technique for things like timing analysis too. So in this one, you'd have to start in the top left because it's the only thing with no inputs. And then you could go either to the right or you could go down. So those ones, they have one input, both inputs.
Nah, I don't like this.
Input's been processed. So you can just say, take the maximum across my input, for example, if you're trying to find the maximum delay. In this case, I'm just trying to find the minimum. Like the minimum cost.
We're trying to find maximum gain here, so it's the same.
You're trying to find the maximum gain?
Yeah.
It's the same. So you start with, you have no input edges, you start at S. You can either go right or you got two choices now whose inputs have been processed. They just look at what is the cost of my input or the value of my input, which is like, say you set S to 0 and they say, okay, it's, the edge weight plus whatever was on S. And now they know their weight.
Mm-hmm.
And now that node right below them can go because both of its inputs have been processed. You never backtrack.
Yep. And so therefore you only visit a node once, ever.
So the Dexters wouldn't be too bad here either.
No.
You do Dexters by like basically adding whatever the most negative thing is to every edge and it effectively just sorts it on the fly.
Yeah.
Rather than having that like sort of fixed sort of.
But it's just a very efficient way of doing legalization. How are we doing on time here? Oh boy, okay. So global placement optimization by local partitioning. So this is an extra step. So what they've done is they did their solver. They do their legalizer on all the movable blocks, and now they want to get just that, they want to milk out that last little bit of HPWL. So what we're going to do is we're going to perform what they call local partitioning to further improve the quality of using, by using FM partitioning on neighboring cells in each row. So how do they do this? They scan the global placement from the top row to the bottom row, from left to right. Then they go for each two adjacent pair of bins, they treat those as an initial partition. So I have my two bins, I have my initial partition, and now what I'm going to do is I'm going to use the FN partitioner to repartition the cells along the cut line by minimizing the edges cut between the two bins, subject to the bin capacity and row size constraints.
So in some number of cells they chose.
The bin is just, they cut the rows into bins. So there's a row time column number of bins. And they don't remember what they set for the column size, but I assume it's probably the same as row. That's my guess, but I'm not sure. But as you can see, this is kind of expensive. And they repeat the scan continuously until it doesn't improve by some threshold, which they call B. So they will continuously scan over the entire space and continuously try to do this partitioning approach. I'm a little scared by this because this is the order of the number of bins multiplied by the time complexity of doing FM times number of iterations. So this is a very slow approach in my opinion, but it must have given them enough gains to make it worth it. So that's just a little bit of a touch-up they do on the global placement. Again, as you can see, this is very different from what analytical placement normally does, where we'll probably legalize and then do something like this. They're really just trying to continuously look outwards, do global placement on using analytical approaches and then legalizing. Now they go inwards, and now they're doing some local updates. And they're doing this inside global placement. This is that hybrid approach that they're talking about. And then finally, we have our detailed placement. So all of that was global placement. We've relaxed the constraints to just bin capacity constraints and row equality constraints. Now we want to convert the global placement into a detailed placement, so there's no more overlap. And they do this by greedily applying detailed placement constraints to the global placement while maintaining the relative ordering of cells. What does that mean? I have a row, and I have a bin that's overfilled, but it's below its capacity. I can see that it has cells A, B, C, and D. I'm going to make sure that A, B, C, and D appear in that order, and I'm just going to spread them out such that they're not overlapping anymore. And the key idea here is that they maintain the ordering of the relative ordering from the global placement. And they also assume that all the cells are touching. That's the assumptions they make.
Why is it illegal if they're under their capacity? They just have like.
That was in the global placement. That was part of their global placement formulation. They declared that global placement is legal if and only if you meet your bin capacity. I think it's part of the optimization.
So this, below that, they didn't really worry about it, like the X's might have been overlapping.
Yeah. Yep.
Okay.
Exactly. That was their distinction between global placement optimizations and detailed placement. They allow overlap in global placement. They don't allow overlap in detailed placement. And the next step for the detailed placement, and this is going to get fun, they create a window at the beginning of the first row in the placement. This window is approximately 2 bins. And what we're going to do is we're going to perform optimal interleaving. That means, and I'll explain the algorithm in detail, they're going to take the blocks in here and they're going to interleave them to try and optimize them further. They then slide the window along each row from top to bottom. It's very similar to that the FM partitioning we saw before, and they're going to do this optimal interleaving. They're then going to cluster the cells into each row such that the size of each cluster is between hyperparameter L and U. And then guess what they're going to do? They're going to do the exact same thing again. Window goes through, they do that interleaving, but the idea is that because I've clustered things, I get a more global view of where things are going to move. And then they uncluster the placement, and then they start it all over again. They repeat the process over and over and over again until some criterion. So what is this optimal interleaving? And how is it optimal and how is it interleaving? So for window W, which they set to be twice the size, twice the size of the average bin in the global placement, find a subsequence A within W, and then let B be all other cells. What does that mean? I have this window and it has these cells in it. I'm going to create A, which is this one, A1, A2, A3. It's a subsequence. I'm not going to allow them to be reordered. I'm going to lock in that A1 always comes to the left of A2, always comes to the left of A3, and then B are all the other cells. What we're going to do is partition them like this, boop, boop. And what we're going to do is interleave the sequences of A and B, but keep the relative ordering. So A1's still to the left of A2, but we're going to shuffle them together like a deck of cards. And we're going to solve this using dynamic programming. The idea is that we want to find an interleaving that minimizes the HPWL. And they claim it's an optimal interleaving, and they solve it using dynamic programming. And they claim it's solved in polynomial time. You can see the paper for an argument as to why it's polynomial time. And I do want to make a final note. They set the magnitude of W to be twice the average number of cells in any global bin. So basically the window size is about 2 bins in width. That's kind of the idea you should get around here. And I didn't go any more detail in this. So you can see the paper for more on this, on how they prove that they get optimality and stuff like that. They talk about that in the paper. The idea is that they're really just shuffling things around. This is a detailed placement optimization to try and get more HPWL after we've legalized.
When you say find a subsequence A, do you mean actually have an algorithm to find something, or
Yes.
just find?
I believe they actually find something that's optimal. And they talk about this using a dynamic programming approach. Again, I also didn't really understand it, so I didn't want to put them in the slides. It's a little strange to me, but that's why I believe it's polynomial time. I looked at their formulation. They're using memoization. They do have optimal subproblem. At least they claim they have optimal subproblems. So it's probably dynamic programming, but I'm not sure. So yeah, again, this is just an optimization they performed for detailed placement. And now here's where they gave the overview of the entire algorithm. And here's where I'm going to do the same slide again, because I think it's super helpful, but in less detail now. So global placement can be seen as an iterative improvement algorithm. We started with an initial placement, and we're going to iteratively improve it by selecting a subset to improve. And this subset will decrease over time. We're constantly shrinking the number of elements we're considering movable. We're going to optimize it ideally, ignoring constraints using that LP formulation. And then we're going to legalize while only accepting moves that improve wire length. So as we're doing those ripple moves, we only accept moves that actually improve the wire length. And then detailed placement iteratively improves the fully legal solution after global placement. And it tries to interleave cells between their neighbors to try and find more optimal positioning for them for HPWL. And that's the overall flow. And you can see all the hyperparameters that are involved. As Vaughn noted, I didn't even notice this alpha right here. So, in the paper, they do mention what alpha is. How are we doing on time? About 4 minutes. I'll come back for that. But that's the overall algorithm. As we can see, it has elements of analytical placement and elements of things like simulated annealing, where we're just trying to do moves and accepting moves and rejecting certain moves. Except I don't really see any places where they formally reject moves. So it's just kind of interesting. Here are the results. Notice there's no runtime results. That's in the next slide. I'll show you. They don't compare the runtime of their flow to anyone else. They only compare it to themselves. And we can see the quality improvement over other works. This is Timberwolf, this is Force Directed, and this is Snap-on. And we can see that Mongrel, and there's a little note here, the best among 10 runs. I'll show you what this means. Remember, there's randomness in this algorithm. I believe, unless they're non-deterministic, which I don't believe, I believe they're doing 10 different runs with 10 different seeds and getting the best of the 10, I believe. Which is, I don't don't know if I agree with that approach, but they did it. And I'll show you the results, and they also show the runtime for different like best of 5, best of 10, and so on. But as we can see, the improvement in HPWL is about 16 to 17% compared to the other state of the art. And this was back in the year 2000, just so you're aware, for ASICs. We go back, and one last thing I want to show, the size of the circuits. So this one, these are MCNC, this is 800 cells. The largest one is 25,000. I want to repeat, the ones we're working on are 500,000. So we're about 20 times bigger than their largest ones. Just keep that in mind. Yeah, exactly. Oh yeah, I'm thinking of movable cells, you're right.
To be fair, our computers are also like 100 times bigger.
They were using a 300 megahertz machine. We're using 1 gigahertz. I don't know.
1 gigahertz.
Have you used winter meat recently?
When you look up second from now, I think that computers got 100 times faster from 2000.
Have you heard of Moore's law, Vaughn?
They are faster. That's like England's exaggerating.
Yeah, this is not parallelized as far as I can tell.
But I mean, you can look.
Yeah, I mean, but like from 2000 to like 2007, we did have more.
But do be aware, we care a lot about scalability, not raw runtime numbers. So it doesn't matter whether it's 100 seconds or 50 seconds. What matters is that as we get to bigger and bigger circuits, how much worse it gets. Here's the last table I'm going to show today. So these are, as I said, they get the best of 5, best of 10. And you can see how the quality changes. It's interesting, to be honest, that they show these type of results, but we also finally get to see at what their CPU time is. And this is 2 hours,
Yeah.
2.5 hours-ish. And as we can see, the really small one, Prim 1, which was 800 nets, or 800 cells, is taking around 160 seconds, which is actually, it seems kind of high, but remember, this is the overall flow. And then it goes up to 3.5 hours. So this is getting pretty expensive, especially because if we look at the size of these circuit differences, this is about 25 times difference. And this runtime is about 76 times increase. So that's pretty substantial, I would say. They also do not give a breakdown on how much each step takes. I would love to see how long the detailed placer takes relative to the global placer and so on. They do not present this in the paper. And this is my last slide. I provided some resources for people who are interested. So Mongrel is at the top. And this number 2 is an article which describes the LP formulation of relaxed placement for this paper a lot better. That was the 2002 one I talked about. And then finally, this is on the network flow-based min cuts. This is the one that I claimed has big O of V plus E. And they do a much better job explaining how they set up their graph. So these are just some papers you might want to look into, but that is Mongrel. Any questions?
That's cool. I'm trying to look up second over time. I think I have it right there somewhere.
I think we put the graph of that in the in our recent paper one.
Did you put that in there?
It's in the slide deck, I think. Is it not? We have the single core performance.
Carol, did you put it in the final version or not? Did you put it in the slide deck for the?
Do you remember that? I remember that.
I've sent the ladies version.
Yeah, we updated it using you gave us
We
an
did put it in.
yeah, we have an Excel script and
We could, if you bring up your presentation. we
You know what?
can check how much faster.
we'll derail the reading groups. I don't mind. Where would I find? Oh yeah, my website would totally have this. There's slides. And
We have to people guess before you look pretty up.
oh yeah, what are the guesses? Here, let me get out of
My
here.
10 is probably a little too low. I think 20 is fine. So.
Vaughn's at 20. Do I hear 30? Do I hear 30? 30 in the back.
Okay, fair enough. Came down, I think I got.
Yeah.
Okay, 50 versus 20. Anybody else want to? 30? Okay.
Okay, so serial CPU performance.
Oh, wow.
Thousands
That's a lot
to.
of
100.
100. Wow, I was right at first.
Well, no, that's starting at, it's not starting at 2000. So the first factor.
Oh yeah, it's 5. So it's 20.
A factor of 3. It's a long scale. So 100 divided by 3, it's not bad actually. 33, you get it.
Yeah. This was a great slide deck, actually. I like to be able to point back at it. But yeah, so Mongrel's a very interesting work. I really wanted to use their LP formulation for VTR, but I don't know how to reformulate it with net weights because the flow, I don't know how to change the edges in the flow graph to make it act the way I want. And if we can't make anchor points, it just won't work. The ripple moves are very interesting though.
Yeah, there are. You could take the general technique of rip up, like unfix a bunch of things, basically move them around, like, you can solve it in a bunch of ways, like with an analytic solver, you can also treat it as kind of an assignment problem. which
Right.
people often do as well. And then ripple it to get it legal. You could put that in as a form of move in the annealer too.
Yep, I actually noticed that as well. This is why the ripple move I thought was originally a partial legalizer according to our notation. I then thought it was a full legalizer according to our notation. Then I thought it was a detailed placer. I found out it can actually be used as all of those.
Would be a good thing to put that in. It was actually in, like, if you read like the reinforcement learning placement papers, by like Mohammed and others in the group. They list things like windowed placement, like assignment problems as useful move generators, which we've never done. But they would make sense.
Hmm.
And you could choose, like, the way they choose this is like they pick a net and they say, okay, take all the things connected to this net and make those move.
Mhm.
Like, some of the things that would be very interesting would be take the critical path.
Yeah,
Take a bunch of critical connections that are connected to each other or the entire path. They're all free to go. And now reassign them in some intelligent way, right?
Yep.
Maybe for min wire length, maybe for.
yeah, there's nothing special
something
about these
more
game turners.
focused on timing. And ripple them to make them legal and see what you get.
Yep,
It'd be a relatively expensive move, but basically. You could put it in the annealer and have it decide, like learn basically, when should I choose this move? And it's relatively expensive, but it can be powerful, especially like trying to. Well, like trying to improve timing, that's one I kind of stand there. Basically take a bunch of critical connections that are connected or an entire timing path and say, try to fix this.
yeah, and when it comes to the time complex or the runtime of this, a lot of the time is actually spent building the game graph. So if you can cache that or store it somewhere, and every time you do a move, you only update the gains of the things that moved, you can probably do that very efficiently. But if you do this as part of simulated annealing, you need to somehow enforce that that gets maintained.
I don't know if you'd have to.
Because regenerating that for every single move could be very expensive. So that's why when I envision making
I probably wouldn't try to maintain it. It probably wouldn't work well.
well, then how regenerating it would also be very expensive.
I mean, the move, it depends. If I'm only doing this on critical paths laid in, it's, if the move is expensive, it may still be okay.
Fair enough. Because you have to remember, I had to pretend.
Maintain that. Pretty expensive.
Agreed. Because the way we got this, remember, we had to pretend like I moved each one of these one by one and recompute my cost function, which is HUWL. Now you can do this more efficiently because you know the nets that have changed, so you only need to get those differences. But that's still very expensive, especially if these are high fan out nets potentially. So something to keep in mind. Although finding that max gain monotone path can be very efficient, you got to make the graph.
So you said that when you you do the -1 from the S to the thing under it.
Yep, this one.
Yeah, so you do that and the gain terms change, and it might be like better for the -1 to move and not the 4 to move, right?
No. Oh, sorry, for -4? Yes.
No. I mean, like, so.
Oh, when I move this down, it
Yes.
may become better, yes.
Maybe better than 4.
Or maybe that was a bad example. Let me give a better one. Let me see if I can find a good number for this. See this one that goes 3 down? If I bring this one down, notice that I have a -3 here and -2. Most likely when I move this one down, moving it right is probably a better idea than moving one of these two.
Yeah, but here's the question. So when you do this recalculation, could the path itself change? Like not just what
Yes,
is moving, could
and
the path itself change?
They talk about this and they said that if you were to move a block and the gain were changed, so for example, this 4 change,
You want to go down.
yeah, it can never happen. That can never happen because the gain can only ever increase from the right. And they talk about this in the paper. Oh, I see what you're saying. What if this 3 became way bigger?
Yeah.
I don't know actually.
Like 10.
And then all of a sudden this one, I think they don't think about that case. But they do mention that they take it into account.
I don't think I understand this case. You're saying like the game will change as you move something?
So yeah, you do the -1 move from S to the block to the node under it.
Yeah.
And then the gains change, and so
Oh, I see what you're saying. They do handle this. I just remember this now. He's saying that what if I now want to move this down? The thing is they don't allow that. They will only say we have to go right now.
Right.
Who has the best one who has to go right? And the idea that they talk about that says this is okay is that the gain of this path would only go up. Because the only way you would do anything other than the one that's 4 here is if you found a better one. So they say the max gain one will only get a higher gain. And so you're right. They don't exhaustively search, okay, what if I then move this one and then do the other one? Will then the max gain optimal path be all the way down, all the way right?
It might not be like the.
It's definitely not the optimal. And also, remember, we're doing a monotone path here. If I allowed it to go up and down, left and right, oh, I could move everything all over the place.
I
But
don't think it really matters in this case, like you do the move and then you want it to go right, but now you see, oh, if I go down.
oh, I can name you an example. I move it down, right, and then let's say there was a bunch of things here that really want to go up. Then they
I
go
don't
up.
know that. Just down. You're there and you wanna go down now,
Yeah,
so that changed the path, right?
sure, but they say fix the path in their algorithm. And I don't think they're claiming optimality here. Not, I'll note the word optimal is right here. Don't look at that.
I know that lives, that you step back up. So, okay, so I moved this, some block here, right, down.
Yeah.
Okay. I have gains for all the blocks that are here.
Yeah.
Right?
So
And I
this
guess I have to
new
compute
block-
my new gain for the block I just put there.
Yes, you
right?
do.
So I gotta compute that. The gains for the blocks that were already here. Okay, so this guy, if I move him down, maybe he's connected to this one that I just moved down, okay? If he is, he already had moving down stretch to net, okay? And he still has moving down stretches in net, right? Because he's connected to this guy who used to be there, but is now here. If I move down, I still stretch that net. Does this make sense?
No.
Okay, well, let's consider, I guess I'm trying to figure out what case, I don't see the case in which these gains are out of sync, right? So maybe you tell me what, the reason I think they're in sync is because of the fact that this is all wire length, okay? So they basically go, I've got, this guy is connected to a bunch of other things, okay? That's what's making the gain for him to various directions, okay? He's got a bunch of things connected over here, then he's got a positive gain. It's gonna be good for him to move that way, right? And if he's got a bunch of things, let's take down going down. He's got a bunch of things connected down here, he gets a positive gain for moving down. He's got a bunch of things connected up here, he gets a negative gain for moving down. Right? And all the things that I haven't moved, nothing's changed.
Yeah.
All those pre-computed gains are the same. The only thing I moved is one block up here, moved down here. Okay? So if this guy was connected, if I wasn't connected to him, then obviously my gains haven't changed, right? Because I don't care that he moved. If I was connected to him, well, he used to be above me. So moving down would cost me, okay? He moved down to be beside me. Moving down still costs me, okay? I don't need to update anything. Maybe I want to move to the right. If I was connected to him before, moving to the right costs me. If I'm moving down, well, yeah, if he moves down here, moving to the right still costs me.
Mhm.
Now, I guess there might be a case he moves to the right. Like he moves to the right, then I am out of date.
Yeah, but you can never go
Think-
left.
Well, I guess because it used to think that it would cost me one to move over here, and now it doesn't. But the thing is, by moving here, you're no longer considering this one.
Yeah.
So this one is now, that's kind of like this,
Ah.
don't backtrack. It's like, well, yes, my gains are out of date, but I can't get back. there.
And that's the argument for using a monotone path. You can actually guarantee that. Ah, for HPWL, maybe timing gets things makes.
Yeah,
things
so like
better.
you change just to stuff like timing and stuff, and I think all bets are off.
Oh, yeah.
right? Like,
It's still good. It won't be bad, I don't think.
Well, I mean, you can use sort of similar concepts, but like some of the trickery may not work.
Yeah, definitely the trickery here will not work. Like I've already talked about the LP solution won't work.
You're moving it, if you had a timing path and you're moving. Actually, I'm not sure.
That could get-
You think of it.
That could get nutty.
You can still think of it as a bunch of springs with that kind of like wire length, but you have to sort of think about it again and go. If I'm moving along the directions I'm being pulled, maybe it's okay.
Hmm.
But
Any questions online before we end? Because I realize we're over time. Awesome. Anyways, everyone have a great afternoon. Thank you guys so much for listening.